Okay, so today we're going to talk about the gates of times. This is a joint work with our students, Daniel Katzman and William Hoshek, which I think is here. And they did most of the work, so thank you for that. And also with Chitchanok and Yuval, which has been a pleasure to work with. Okay, so basically, these are two terms that probably everybody in the audience already know. There are cache side channel attacks and there are speculative execution attacks. And what we've seen over several years is that how can we use cache side channel attacks in order to create speculative execution attacks. And if you look at Spectre and Meltdown of those other attacks, they usually use microcontextual side channel as one of the gadgets where we can basically use them to leak the information, or basically to learn the information that was leaked. And in this paper, I wanted to ask, what about the other direction? Can we exploit speculative execution in order to improve cache side channel attacks? And the reason that I'm standing here now is because we managed to answer it positively. And now we're going to talk about how and why. So basically what we're going to talk about is how can we view microarchitectural states as logical states? How then can we use transient execution to create logical gates and actually do computation on the microarchitectural state? How can we use it to build logic circuits for fun, which is nice because it's fun, and how we can do it for maybe profit, I'm not sure. Basically, how can we use it to amplify side channel attacks and to show a very nice novel attack which we call prime and store. Okay, so by now you mostly all over your world, we have memory, we have cache, we have processor. And basically what we can do is we can associate a logical value with every memory address, which basically means we give the value true if the memory address is in any one of the layers of the internal cache, and it's going to be false if it's not cache. So of course, most of the memory will have the value of false because the memory is much larger than the cache, but some values are going to be true. And now we can start playing around with it. For example, we can use CLFlash or other mechanism to flash out an address, and then we can change its value from false to true. We can also just access a memory address, and then we're going to change its value to true because it's been fetched into the cache. And we can measure if it's true or false by measuring the access time to an address. And it also implicitly set the value to true because every time we access an address, it's going to be fetched into memory. Okay, so this is very trivial, and now we need to try to convince you why it's also useful. So now, what else can we do with it? So we can try to look at this very simple conditional branch. Basically, we're going to check if some input address is 0, and we're going to return. Otherwise, we're going to access some output address. And again, accessing this output address is going to fetch it into the cache. And now, if true, if input is not equal is 0, then of course we're going to run the other code line, and the output address is going to be true. And now we can ask ourselves, what happens if the input address is 0? And the answer is now not that simple, because basically we have speculative execution, and this is a branch. So evaluating the branch condition can take some time. So the CPU is going to try to predict what is the future execution. And if it predicts correctly, then of course, okay, great. If not, then we're going to have what we call a rollback. We have a speculative window, we try to run some comments, we see that we took the wrong branch, and now we're going to roll back all the computation that we made, but the macro architectural state still remains the same. This is the basis for all of this Spectre, Meltdown, and other attacks. The main idea is that this line of code might be executed even if the input address value is 0. So if we look at this speculative execution of conditions, the speculation terminates whenever the condition is resolved. And in order to resolve this condition, we need to know the value of the input address. So we're going to set the input address to be 0. We're going to train the branch predictor to mispredict, to assume that this is 1. And now, if this input address is inside the cache, we're going to resolve the condition very fast. And then we're going to return before we access this output address. And then it's not accessed. However, if the input address is not in cache, it's going to take a very long time to get it out of the memory to resolve the condition. And now we have a long speculative window, and we're going to speculatively access the output address, and thus setting its logical value to true. And what this means basically is that we can have this truth table, where if the logical value of the in is true, we get false. If it's false, it gets true. And this is not very easy, not very hard to see. This is basically a NOT gate, which we implement on the microarchitectural state of the memory. Now we can try to look at other examples. For example, we can take multiple input values, and now we can again make the truth tables. And if you did your electrical engineering courses, you can see that this is a NOR gate. We can also try to look what happens if we sum those two addresses. And then if this truth table, this is something that is a very nice gate, which we call NAND. Now, if you did this basic course in electrical engineering, you know that this is a very, very interesting gate, because from this we can actually build and implement any gate or circuit that we want. So we can have what is equivalent to a full Turing complete calculation on the microarchitectural state, which is fun, at least for me, also for you. And also, we can try to have multiple outputs, like what we call fan-out in the gates, simply accessing two memory addresses. And this is actually needed because when we do a computation, each time we use a value as an input, we're going to destroy its state. We're going to also set it true because we try to measure it. So if you want to use the output of one gate in several other gates, we're going to require a large fan-out, and this is something that we can easily achieve. And we have some limitations because of line fill buffers and other CPU parameters, but this is not very important, and we can have relatively large numbers of inputs and outputs, which again is fun. We can also do what we call a minority report. Basically, we can translate these large truth tables to the not of the majority. So the nice thing about it is because we can do it relatively efficiently, and this is actually something that allows us to do error correction in the microarchitectural state. And because we have noises and we have other processes running and stuff like that, it's always nice to be able to run our computation several times and do a majority vote, so we have error correction, and we can do stuff very robustly. Okay, so I hope that convinced you that this is possible. It's nice. So let's start with the fun. So we can actually implement a simple ALU. It's about 1,000 gates. We get relatively nice accuracy when we're trying to do computation like addition or subtraction. Not very useful, but again, fun. We can do cryptographic computation. We can do one round or even full SHA-1 computations inside the microarchitectural state. And we can do a game of life. This is actually the heat map of 16th generation of game of life, and it's relatively accurate. So again, fun. But we also want to do a little bit of security. And now we're going to talk about side channel attacks. And one thing about side channel attacks is that we usually require very high resolution timers because we need to differentiate between memory or cache line that is inside the cache or not, and this is not a lot of nanoseconds. And actually, a lot of mitigations, like in browsers, rely on the fact that we're going to limit the resolution of the timers in order to prevent and mitigate this type of attacks. We have many attacks that try to actually re-find high-resolution timers in browsers, and we have a very nice cat and mouse game, and we have a lot of papers, which is good for academic people. But one of the questions is that what we can show here is that basically, we don't need this. We can actually use very low resolution timers and still run cache attacks. And we're going to show how. And we have the prime and store attack. And the nice thing about it is when we use amplification in order to use low resolution timers, we basically lose temporal resolution. We can't probe many times per millisecond, which makes the attack less practical. So maybe still limiting the resolution is useful for some mitigations. And again, we show that this is not the case because we can have a novel attack that we can actually probe the cache line state with a resolution that is much higher than the system clock that we can use, which is also fun. So, amplification. Basically, we can have a NOT gate with a large fan-out. And what we can do is take the state of a single cache line, and we're going to copy it to several, or 8 cache lines in this case. So we amplify this simple measurement. And now we can repeat it and do it like a tree structure. We can amplify to 64, 512, 4096. And now we don't need to measure the time difference between one address, if it's in memory or not. We can have 4096 addresses, which is much larger. Now this has some limitation because we can't amplify to something that is larger than the cache size. So we have a more advanced arbitrary structure that we can do it for a much larger number of cache addresses. And basically we can amplify a single cache line, if it's in cache or not, to a resolution of more than, in this case, 100 milliseconds. Then I think this is fun. And we can also do it in browsers, which was the main use case. So we implemented it in WebAssembly, and we were able to find eviction sets in Chrome using its native 0.1 millisecond resolution timer. It takes a couple of minutes to find the entire eviction sets in memory. And finally, we want to have high resolution prime probe, although we have low resolution timers. So what we can actually see is that probe in prime and probe attack is implying a NAND gate. We simply take all of the addresses inside the eviction set, and if a single one of them is not in cache, we're going to want the value to be true. And what we can do is user gate. We repeatedly, with high resolution time, probe the same cache set, and we're going to store the result in different addresses. And then when we finish the attack, then we can amplify each and every address. We can use our error correction code in order to handle noise. And we show how can we attack square multiply of El Gamal with a 0.1 millisecond clock, when we patch a lot of measurements together and get the values. One small thing is that I found very nice is that recently there's been a lot of related works doing very, very similar things, which I find exciting because this is an idea that its time has come. And actually, one of those papers, we find out when we did a disclosure with some guy in AMD actually did very similar concurrent work. And there are a lot of other papers. In summary, this is fun. We can use transient execution, and we can improve cache attacks. And in that, I will be happy to answer any questions. Thank you.